about stochastic control. Used to be a KFR, currently an IIT.
So thanks Sandeep and Hari for inviting me for this event, and also to apologize to people who have heard my previous talk on bandits. Here there will be some overlap, though not hopefully not too much. So this is basically reinforcement learning algorithm, but kind of specialized for applications to restless bandits. And to make, should add that joint work with Karan Chadha who is here. So I'll give some quick mini tutorials on one particular algorithm in reinforcement learning called LSP, which stands for least squares policy evaluation. And then another quick tutorial on restless bandits. Then I'll talk about the proposed RL scheme which we have, and an application to some web crawling problem which is formulated as restless bandits. Okay, so I'll just describe what I mean by reinforcement learning. Of course, the origins of the subject are in behavioral psychology, etc. But for me, it's just a algorithm for approximately solving dynamic programming equation in control. Okay, so the system we are trying to control is typically a finite state Markov chain with discrete, that is a finite state labeled 1 to n. And what I'm going to consider is, I said that the algorithm LSP stands for least squares policy evaluation. So the two levels at which you can use reinforcement learning. One is, as I said, it often used for approximate solution of dynamic programming equations, either online or offline based on data. That tells you how to optimize the system. The sort of lesser objective, but is often important, because sometimes forms component of the overall optimization scheme, is to just evaluate a policy. So if you have, for example, some guess for a good policy, or somehow you have arrived at some policy you believe might be optimal and you want to evaluate it, then what you want to do is just estimate the performance of the policy. So it's a simpler problem. You're not optimizing, you're only estimating a certain quantity associated with the dynamical system. So that's why I'm considering a Markov chain and not a controlled Markov chain. So this is right now just a pure uncontrolled Markov chain. So as I said, it's a finite state, and transition probability matrix P, which I assumed to be irreducible. So there's a unique stationary distribution pi, and Gij is the cost. I actually messed up one thing already. I shall randomly switch between cost and reward. Because the Brittle index is usually, at least by Brittle, it was introduced for rewards, but I work, being a poor academic, I have been cost minimizing most of my life. So I'm sort of hardwired to think of cost rather than rewards. Okay, so let's start with the cost problems. You want to minimize something, some average cost, and Gij is the cost of going from state I to state j. Okay, so equivalently, I can take a one-step conditional expectation as a mathematical convenience, and see, Gij depends on the current state and the next state. I can just get rid of the second dependence by just taking one-step conditional expectation. So Pij is the transition probability from I to j. So I will treat this as the sum over j of Pij, Gij as the cost associated with I, so averaged over the next state. And the average cost is basically you want to minimize the long run average, so time average of the cost as t tends to infinity. And under the assumptions which I have made, irreducible and unique stationary distribution, etc., it's just the average of g with respect to the stationary measure. So it will basically, that pi stands for, the pi g will stand for this. So this will be the average with respect to stationary measure, some j, Pij. So this is what it will converge to, and that's what you want to estimate. Okay. So what one does is to define this differential cost function. So it's converging to eta star. The average cost is converging to eta star. You subtract that off. You expect this quantity to remain finite, which actually not always true, but for finite irreducible case is true. And I call that hi. This will although the stationary expectation that eta star doesn't depend on where you start because the sort of the process mixes up everything, but this will. And what it does is that it satisfies something called a Poisson equation. So this the name comes from potential theory, where continuous versions of such things appear. So this vector equation, H is a vector, H1 H2 dot dot Hn equal to G is basically the sigma Pij Gij summed over J minus eta star. E is just a constant vector, all ones 1 1 1 1. Eta star is a scalar, and P is a matrix operating on the stochastic matrix operating on H, so it's all consistent. So this is a linear system, and again under the stated conditions, one can show that. See, if I add some constant H to every component of H, it makes no difference. It will just cancel off. So H is unique only up to an additive constant. So if you pin down the value of H at say state 1, then that makes it unique. Eta star is unique always. So eta star is an unknown here. So there is an equation in H and eta star. You are solving for both. And once you solve it, eta star is the optimal cost. That's uniquely. So here, of course, there's no optimization. So eta star is the average cost. Okay, so this the problem is that I mean it's a linear system as good as it can get, but the thing is that the problems are usually extremely high dimensional. State space blows up quickly, particularly in engineering, certain engineering problems. The kind of things I have typically looked at are in communications, and there I mean you often have these queuing models of sort of networks of queues, and if you think of a say, even if you say truncate the queue length at say capital M, and you have n such queues, it goes as m raised to n. So it blows up exponentially and very fast. Even a few queues can become unmanageable for computational purposes. So that's I mean, it's not the abstract mathematical object, namely a linear system, which is difficult, but the size thereof. So what one often does is what's called function approximation. So this is a specific functional approximation. So the idea is that you are trying to solve for H, which is a function of a very high dimensional space. So you simply the general function approximation scheme would be something like this, where I take a beta will take some finitely many values, and this m will be typically much smaller than the state space. Okay, so some moderate size. So you assume that it has some functional form parameterized by a much smaller number of parameters, and try to learn. It's an approximate scheme, but that's best you can do. So that's try to find a good family of approximating functions and try to learn within that class. So what I'm looking at is a specific case, which is perhaps the most popular, which is the linear function approximation. So I assume that H is well approximated by something of the form phi times R, where just to show you what this means. So H is an extremely high dimensional vector. So phi, of course, has to match the number of rows. But the idea is that you pick R much smaller. Okay, so this size will be way smaller than this. And phi is fixed, and you learn only R, you learn the weights. And what's so basically mathematicians would call it basis functions. The AI community calls it features. Typically, you try to choose phi cleverly so that it captures what's essential. That's partly art, and there's a lot of work, separate work on how to come up with good features, etc. But of course, in case of having any better knowledge, you can take the usual suspects, the polynomials or whatever, wavelets and so on. Okay. So LSP algorithm is actually taken from here. U and Burtsika's convergence for some temporal difference methods based on least squares. And the idea is the following. So this is what you want to estimate eta, the eta star with the limit of eta t tends to infinity. And what one defines is something called temporal difference. So this is the, so if you look at the Poisson equation, let me just write down one particular row of it. So it will be hi equal to so this is what you want to be true, and now you have replaced this by phi equal to dot dot dot. We'll get okay. This you don't expect to be true, but you hope that they're close if it's a good approximation. So this minus that would be the error you want to control. And what you can think of the right hand side is a kind of a empirical error. So in the sense that this is a one step conditional expectation. Suppose instead of that I just plug in without taking the conditional expectation the function of the current state and next state. So for it's easier to describe here. So instead of Pij, Gij, suppose I just observe the Gij at time n. That would be g of xn, xn plus 1. That's what you cost. That's the cost you paid for going from xn to xn plus 1. Okay, and similarly, so this corresponds to first term. This last term corresponds to this object. The second last would correspond to the one on the extreme right, and the first one is of course corresponds to this, and then this is offset. So that's roughly that's basically the empirical error. If you average this out, you would get the difference between the right and the left hand sides. And then you try to suppose you want to minimize that. So suppose at time t, I just take the total error up to time t and minimize that over r. I would get this r delta t. Okay, and then this is the typical incremental, what's called stochastic approximation or Robbins-Monroe scheme to learn that. So that requires some conditions. What the CN, the step size CN, or again the jargon changes with the subject. So the stochastic approximation people call it step size, and AI people call it learning parameter. So it goes back actually to 1950, 51 or so. I keep harping on this because that fact is often forgotten. You look at recent papers in AI, they think it was invented in 1980s or 90s or whatever. So this Robinson-Monroe came up with a very clever scheme for this. They actually had their statisticians. Their objective was to solve a nonlinear equation hx equal to 0 given noisy measurement. So some black box which given x gives you hx plus noise. And anyway, I won't go into the details of the scheme, but the clever thing was the choice of step sizes, which they impose certain conditions, and that actually what made it work. That is, sum of Cn is infinite, sum of Cn square is finite. So it's a slowly decreasing sequence, and what this ensures is that actually, at least under reasonable conditions, these algorithms converge with probability 1 to the desired point. And one way of, okay, maybe I will write. So this is the generic Robinson-Monroe algorithm plus Cn hxn plus noise. And there's a viewpoint which came much later was to treat this as a noisy discretization of this or noisy Euler scheme for the differential equation. One can justify that under some conditions, and then what one can show is that the iteration tracks the asymptotic behavior of the differential equation, and that's how one often analyzes these. Okay, so this is the actual LSP scheme, and anyway, so these are the various quantities calculated. I won't. The next slide will make it clear, so I won't go into the details. So the idea is that you are solving basically a projected form of the. You are solving a different linear system. Okay, that's what it does. So you could. So T is my dynamic programming operator. So the linear system which I originally wrote was of the form h equal to th. So it's a fixed point of some linear operator t. And what I have replaced it by is something like this. Okay. So what this is going to do is, once I assume it's of the form PR, it's whatever you are going to get for any choice of R is in the range space of the matrix P, okay, which is not the full space. So this will be approximate. And the other problem is that if I apply T, the image need not be in the same space. So what this does is to project it back to the space. So that's the equation you end up solving. Okay. And it's basically a online kind of recursive scheme to solve this linear system, and one can show that it will converge to the desired objective. So that was the first tutorial. Huh? Oh yeah, I did mention that. That's unknown. So you end up subtracting some offset. So maybe I'll. So what you have to use is something called relative value iteration. You end up subtracting some offset. So you pretend eta star is so okay. What you have, this kind of special for this particular problem. So it's a good question. So other easier problems like discounted costs, etc., you don't run into any trouble. What I said applies, but this problem is a little harder. It's actually of this form. Okay, this is also unknown, so I cannot forget it. So what one does is the iteration, the non-random version of this would have been non-random and non-approximate. It would have been something like this. You subtract some offset, say some value at a fixed state, or some mean, or some such quantity, or say minimum of HNI, something like that. Okay, it has to satisfy some homogeneity properties, etc. But one can that's known what all offsets will do. So it kind of, if you think of this will typically blow up. I mean, it's not this is not for nicer problems which is like discounted. This is a contraction map and it's a unique fixed point and it will converge exponentially. But this is not. This is only, this doesn't increase the distances, but it doesn't strictly decrease them. So it can drift off. The iterations can drift off. So you keep having to subtract something like this, and then this converges to eta star. Okay, so you do get the correct solution in the end. We will talk a bit about restless bandits now. So the multi-arm bandits, this also goes back a long way. So here I'm considering what's called Markov bandit. So there are some n processes which are Markov chains, and you operate m out of n. You can operate only m out of n. Say n machines, and you can operate only m out of n. So though that, so whatever is being operated, I call it an active arm, and whatever is not is called a passive arm. So this is a kind of generalization of the two-armed. The original bandit had two arms, and that comes from gambling, kind of, or one arm rather, right? One arm bandit, that machine, slot machine. You use it or not use it. Anyway, so this is a generalization of that, and the problem is to how to optimally schedule these. So what's good about these problems is that it's a rich class of problem. It's not, of course, it's not all of the Markov control Markov chains, but it's an important subset thereof. And with some luck, you can get some what's called index rule, in the sense that you can assign to each process a function of its state. So suppose I have three processes x and y and zn, and I can suppose I can come up with functions f1, f2, f3. So that just by comparing f1 x1, f2 f1 xn, f2 yn, f3 zn, I can, and comparing them, I can decide which one to operate. Okay, so such rules are called index rules. So that means there's some index associated with each process, and you just compare them and decide. Now, what the classical multi-arm bandit has a clean solution. So by classical, I mean that if there are n processes, the process which you are not operating remain frozen where they are. So suppose I am operating process 1, and at some time it's at xn, and I stop operating, it moves to some other process, it will remain at xn till the next time I return to it. And for that, there's a well-known index rule called Gittins, and there's an explicit expression for that, and it's optimal. And it was a major achievement. It was an open problem for 30 odd years before Gittins cracked it. But the worst problem is what's called restless bandits. That means even if you are not operating, it evolves in some uncontrolled fashion. You have no control on it. I think discounted. Yeah. Average is somehow becomes somewhat trivial. You end up using only one bandit after a while. I mean, it works, but in a trivial sense. Yeah. Yeah. After a few jumps, you will latch on to one and stay with it. Yeah. Yeah. Because it's long run average. So even if you go for a long time, it doesn't matter because you're living till infinity. So restless bandits, of course, this is a harder problem, and it's provably hard. By that I mean that there's a theorem which says that belongs to some exotic complexity class of theoretical computer science. Forget which. That was proved by Papadimitriou and Tsitsiklis. So there's only a heuristic due to Brittle, and that's actually that. Okay, I'll say a few more things about this. So there's something called Brittle index, which Brittle proposed, which of course one thing one would expect is that if the bandit were not restless, it should reduce to gittins, which it does, and it's empirically verified to be a very good heuristic. It works well generally, and also there's some kind of asymptotic optimality proved by Weiss and Weber and Weiss. So if you let the number of bandits go to infinity in a suitable manner, then you can show that you're asymptotically optimal. But for finitely many bandits, which is the usual case, it's not optimal, but works pretty well. So what Whittle did is to kind of replace the requirement that m out of n each time to on the average m out of n, and then it defines the notion of I'll revisit this in the following slides. But what he did was to define this notion of indexability, and in the following fashion. So he introduces something called subsidy for remaining passive. So if some machine you are not using, so he's working in a reward maximization setup. So now on I'll be in reward maximization. So what you do is you pay the passive guys some money to keep quiet, and then of course you expect that if the subsidy goes from minus infinity to plus infinity, the set of passive actors will go from empty set to the whole space. That's always true. But suppose that that increase of the passive passive states is monotone, then you call it indexable. Of course, now it's called Brittle indexable, and once it is shown to be Brittle indexable, then Brittle index is that value of subsidy for which you don't care between remaining active or passive for each particular. So that's given as a function of state for each process separately, and you compare them and take the top m out of n. Okay, so that's what I just said. So Brittle index is the value of subsidy for which active and passive are equally desirable as function of state, and then the index policy is to operate top m according to the rank ordered indices. And this is not optimal, but it's optimal as the number of bandits goes to infinity and known to work well. This has been used extensively. So this is in some applications, sensor scheduling, multi-UAV coordination. Munzar is going to give a talk here, I think, and congestion control by several people. One of the more recent success stories, non-trivial success stories, was application to cognitive radio by Ching Zhao and a student. And this is something I did long back with Vivek Raghunathan, Ming Chao, and P.R. Kumar. More recently, I sort of had a run on the market with some students and several several quick hits. So the first one you will see because I'm using that. Yeah, you don't have. That's important because that's what simplifies the problem. No, that yeah. Yeah, I don't remember what exactly they have done. Yeah. No, incidentally, I should add that these are not all of that. These are not vanilla restless bandits. There are some complications in, for example, opportunist scheduling. There's also continuous control, so it messes things up quite a bit actually. Anyway, just to sell it a little more, some of these problems actually came from industry. So this I'll talk more about that with a Russian co-author who got it from a Russian search engine called Yandex. And this problem also was proposed by a friend in Tata Consulting Services, and so on. So, okay, so the notation will be there are several Markov chains with finite state spaces. Oh, okay, here can be intervals in put it more generally. They can be real also. What actually one needs is that there has to be some order. And there are two modes, active and passive. And there will be correspondingly two transition probabilities, transition mechanism for under active and passive, and two rewards. And typically, reward for active will be much higher than passive. So this you want to be active, but it's a constraint that you cannot not more than at most m can be active at any time. Okay, and then you have to schedule. Oh yeah, second one should have been RB. And then the objective is to maximize the time average reward. So this nu in is the indicator, which one if ith band is active, 0 otherwise. So if this is 1, if it's active, this is 1, and you get this reward. If it's passive, you get this reward. And the constraint, the original, this sort of hard constraint is that, I mean, sometimes one relaxes to less than equal to m, but that doesn't change things too much. I will consider equal to m here, so exactly m out of n. And that's hard, as I said. So the Brittle relaxation is that you take time averaged. So this sort of looks like your cost, but so you are what it means that you are allowed to use more than m at some times as long as you compensate for it by going under m at some other time. Now, the reason I emphasize that this is looks like the average cost is this fits the framework of something called constraint Markov decision process. So you are trying to maximize one reward subject to constraint on another reward. The important thing is that they have to be of the same kind. Otherwise, you can't solve the problem. I mean, it's not easy. If you have maximizing average reward subject to constraint on discounted reward, that's trouble. But this actually is not that bad.